Now we'll look at the how computer represents um, sign numbers, let's say negative numbers and positive numbers as well. So there are several schemes to represent numbers, but there are two most common one, which is sign magnitude numbers and also the two complement numbers. And the sign magnitudes is simpler, but it has some issues. That's why we're going to learn the two complement numbers next time as well. So let's just go with the sign magnitude numbers. So um, let's say if we have an n-bit system, then the most significant bit is used as a sign. So you're gonna have one bit. So 0 gonna represent positive number and 1 gonna represent negative numbers. Then the rest of n minus 1 bits gonna be used to calculate the magnitude or the numbers like we have computed so far. So what happens is this bit, the most significant bit is gonna be positive or negative, and the other is gonna have the same position. Let's say we're going to have the first position we wanna have 2 power 0, second gonna be 2 power 1, and the next one will be 2 power n minus 3, 2 power n minus 2, and the most significant bit, or the bit of 2 power n minus 1, is going to be used for the sign. So if you see 0 there, it's going to be the positive one, and if you see 1 there, it's going to be the negative one. So let's take an example that we have 5 bits. And for this 5 bit, we want to have two numbers sequence. For the first number sequence, we'll have 0, 0, 1, 0, 1. And its position values for the most significant bit, and it is 0, so it's going to be translated into positive, and the rest going to have the values as usual. Okay? Similarly, when you see 1, it's going to be translated into negative, and the rest going to have the values as usual. Now, if we do the computation, like take their face values times with their position values, to find what is the values that they are representing, we'll find out that this one is representing positive, or 0 plus 4 plus 0 plus 1. This one is going to be positive 5. And for the second one, we do the same computation, but the 1 bit over here going to represent negative, so it's going to be negative 5. Now, sign magnitude is very simple, straightforward, but it has some limitations. Let's just say if we take those two numbers, which is positive 5 and negative 5, and we perform the binary additions like we have learned so far, then we add the first bit, it's going to produce 0 and carry 1. Then we add that carry with 0 bit, and another 0 bit is going to produce 1, and there is no carry. Then we're going to add the next 2 bits. It's going to produce another 0 with 1 carry. And if we add this one, it's going to produce 1. And if we without carry, and then we add the last bit there, 0 plus 1 is going to produce 1. So let's just perform the checks over here. If we translate this minus 1 as minus, this is a number 1 as minus sign and corresponding position values, we're going to times them. Then we're going to get it is minus 10. And we'll see that we add positive 5 with minus 5, we're supposed to get 0, but in this case we get -10. So sign magnitude numbers is straightforward and it is relatively easy to use. However, it is wrong or incorrect. Okay? So we'll have another limitation, let's say, also in 5-bit systems, and we're gonna test with this 2-bit sequence. So this one is 0, so it's indicate positive, then the rest is going to be position values. This one is 1, and it's going to be negative, and we have other position values here as well. So if we do the computation again, this one gonna produce 0. Okay? And if we do the same computations over here, this one is also produce 0. So you'll see that the same decimal value, which is 0, is now represented by 2 different bit sequences. So this one is troublesome. It's going to be ambiguous for computers. And there are two, that's why next time we'll learn the system which is more commonly used for computer, which is called 2 complement.